Today we are planning one lecture on electronics and related area. Just I'm reading a brief summary about you. Dr. Selva Raja is a professor in electronics and communication engineering. Just a second. Dr. K. Selva Raju is working as professor in Department of Computer Science and Engineering in Pondicherry Engineering College, Pondicherry, which is recently upgraded to Pondicherry Technology University. He has completed diploma in electronics and communication engineering in the year 1987 and worked as senior production technician in Pragati Computers, Pondicherry, one of the few computer manufacturing companies in India by then. He has joined PEC as junior instructor in the year 1989 and worked as technical staff member till 1999. He has completed AMIET in the year 1993, MTech ECE in 1997, and PhD at IIT Madras in the year 2010. He has more than 30 years of experience. He was appointed as lecturer in the year 1999 and elevated to the post of professor since 2013. हमिंग आ रही है बहुत. He has a good number of publications in reputed journals and conferences, and presently guiding PhD scholars and master students. He is the Institute Web and Email Administrator. He is also member of IQAC in PEC and Pondicherry University. Once again, Professor, welcome to this session. We are waiting for your lecture so that we can be benefited with your experiences. Once again, welcome.
Thank you. Thank you, Professor Neelam Srivastava, HOD.
Yes.
Dr. Ramchandra Singh Chauhan, and respected faculty members of the Electronics Department and my dear student friends of IET Lucknow. So it is my great privilege to be part of you in this IET IEEE Student Chapter Lecture Series, which we are conducting every Saturday. I think this is the fifth week. Thank you. Thank you for arranging a wonderful, different kind of topics. Though you look at me as a professor in computer science engineering, but by the CV that you have seen, you might have noticed that I'm all along in electronics and communication.
Yes. That is what.
Yeah. So by 2000s and all, there was no much of discrimination, and there were not much graduates in computer science, and that has played us way too much particularly. And one more good thing that I want to share with you is that I had been to IET Lucknow, I think in the year 2019, as part of the TechIP training activities.
Okay.
Yeah, so I delivered a couple of lectures, and one on e-governance, and another on wireless sensor networks to the computer science students.
Okay.
So it was a wonderful experience, and I thank all the director and all professors who were there for extending good hospitality to all the faculty members who visited from Pondicherry, from long distance we have been visiting.
Thank you so much. Thank you so much. Hope we will meet again after this corona pandemic.
Yes, madam. Yes, I would like to meet. Yes. Thank you. So I am given a topic on microprocessors, and I was told that the participants are largely from second year, third year, and final year students, if I'm not wrong. I will present my screen in a short while. Yes, madam. Yes.
So many faculty members and students have joined because today is the examination of GATE.
Oh, okay.
Electronics students who are busy in that, they could not join.
Preparation.
Yeah,
Okay.
but this recording will be available with the students.
Okay. It will be available in
Yeah.
YouTube, I know.
Yes,
Yes.
yes,
YouTube.
YouTube,
Yes, yes.
YouTube also, sir. Yes, sir.
Okay. Yeah, I have seen the previous programs. I hope this is visible. My screen is visible now to all of you.
Yes,
Yes,
sir.
yes.
Yes, sir.
Yes.
Visible.
Okay. So again, once again, I express my sincere thanks to the organizers, especially Professor Chauhan, who has contacted me
Thank
last
you.
week.
Thank you, sir.
Yeah, right. And because this topic is my experience, with 30 years of experience, I was there in the microprocessor laboratory of the computer science and engineering department. In fact, in our college, it is the computer science and engineering department which caters to the needs of teaching microprocessors, imparting hands-on on the microprocessors, not only for the computer science students, but also for electronics and communication engineering department students. It is very rare to see in many of the colleges. It will be the other way. The computer science students and IT students will be going to the electronics department to learn about the microprocessors and all that. But here it is the other way. In our college, we have the tradition that since the establishment of the college way back in 1985, the computer science department is always maintaining the microprocessors and microcontrollers lab, and even today, even in 2021 also, we teach the computer science faculty teach the electronics students the microprocessors. So with that, grip in the subject. So I have immediately when Dr. Chauhan contacted me, so immediately suggested to give this topic, even though my research area is on wireless and sound processing.
Okay.
So yeah, so I organize my talk as follows. So we'll just visit very quickly about the evolution of the microprocessors and microcontrollers, the difference between the microcontrollers and processors, and the interfacing with the need for interfacing with the memory and peripheral devices. And this talk will be mostly talking about external world communications, apart from the systems. So I plan to discuss about the various interface standards, starting from the plain old RS-232C, the UART communications, Syntronics parallel port, IDE, ATA, and all that, SCSI, USB, some Wi-Fi technologies, CAN bus, SSP, I2C, and even I have also planned to talk about some technological growth in the interface standards that are meant for getting connected with the video devices as well. Yeah. So this topic, the title was given as it was given as a microcontrollers, and as you might be aware, microprocessors is a predecessor for the microcontrollers. In fact, the microcontroller houses within itself the microprocessor. So without touching upon the microprocessors, we cannot directly go into the microcontrollers. Even though today any system can be designed with just one microcontroller. So the microprocessors are called as the heart of computers, any computing system, heart of the computing systems. And for electronics engineers, it should be viewed as an integrated circuitry, and it is a digital circuitry. It is a digital circuitry, and this differs from other ICs in that not only analog versus digital, even among the digital circuitries, we can call it as a programmable integrated circuitry. Right? So this integrated circuitry can understand programs written in the machine code, and then accordingly its behavior can be dictated by the programmer or the designers like us. These are the two basic components, basic building blocks of this microprocessor fundamentally. So every microprocessor will have its own arithmetic or logic unit. In short, it is called as a ALU. Then all other sections will be controlled by a unit called control unit. Basically, it's a sequential logic. So this advent of the microprocessors, the history of the evolution of the microprocessor dates back to 1970s, even before most of us would have been born. So even prior to this 1970, there were computers. Of course, there were computers. The concept of computers, digital computers, came into existence. One new model of a computer and all that everything was there. But only the technology transition was taking place. So the very first computer started working with vacuum tubes. Most of this younger generation will not have seen it, maybe only the Wikipedia and other kind of things you can see. But I have had an opportunity to see it in my young ages. Most of the electronic components like the radio receivers, television receivers, even when I studied in Polytechnic, the diploma, so we have even seen, the inner parts of the television, radio receivers, very, very big, very huge. They were all using vacuum tubes, and then the advent of the semiconductor technology, especially the diodes and transistors, replaced the use of vacuum tubes, the electronic circuitry. So it has had many things. So it has helped in miniaturization of the end devices, very small form factor, and the power is also greatly reduced. The amount of current that flows for the same functionality was greatly reduced. And, so before 1970s, I would say 65 to 70. So transistors and diodes were predominantly used, and that has led to the development of the integrated circuitries in various scales. We used to classify them as small scale SSI, LSI, VLSI, and so on. So when the VLSI technology uh, came into existence, so people, the researchers and the engineers of those days were able to, come out with a programmable integrated circuitry, which is what is called as a microprocessors. So basically, it has got a combination logic, such as the ALU, adders, subtractors, comparators, many components that are housed in just one integrated circuitry. It also has had sequential logic, several sequential logic, such as various counters, especially there is a counter called a program counter, which keeps track of every line of the program that we write, and a good number of shift registers, because any digital operations would require shifting of the elements. For example, shifting left by one bit is correspond to multiplication by two. Most of you might have been taught, the students might have been taught by the teachers in the class. So, and not only for that, for taking some logical decisions, shifting operations many times used, and it falls under the category of the sequential logic. Right? So basically, the microprocessor single chip is composition of all these various functional units, ALU, counters, shift registers, and every circuitry is timed with respect to an external clock source. This is a sequential circuitry. Every circuitry need to function with respect to the clock source. So the clock source basically is a free running signal which toggles from 0 and 1 in a periodical fashion. Right? So this period only determines the frequency of the oscillator. This is basically generated using oscillator circuitry, and there are different types of oscillators. And the one that is suitable here is the crystal oscillator, because it gives accuracy to closer to 100%. Even though we have other types of oscillators, RC, RLC kind of oscillators available. So where accuracy will be subject to various operational conditions, whereas the crystal oscillators give more precision, and that is what is required in computers also. So this frequency. So whenever you say a microprocessor mu p, so indicated like this most of the time, luckily. So this is set to operate at a particular frequency. For example, you can operate at 10 megahertz. The very first microprocessor that was used in IBM PC way back in 1980s, that is 1984 if I'm not wrong, was working. There's 8088 processor from the Intel. 8088 processor worked at 4.77 megahertz clock when the very first IBM PC came. And today we are in 2021, we are in the 21st century. And we have the evolution of all these processes. We have from the same Intel, we have multi-core processors, like for example, Core i7 processor, capable of running at even 3 gigahertz is very common today. And so that shows tremendous changes that are taking place in the VLSI technology, which permits the process to operate at much higher frequency from a few megahertz to several thousand megahertz or few gigahertz they're able to work. And of course, it is the need of the time also. Once the digital computer revolution started taking place, especially when the IBM has come out a personal computer that every individual can afford to have their own computers way back in 1980s. That has opened a lot of avenues for applications of the computers. So many software developers came, many thoughts, new ideas, multimedia kind of things, which all required, refining the architecture so that it is able to operate at a very high frequency. And this shows a view of a brief history about the microprocessor, especially the Intel, even though there are many other microprocessors available. So this, tells the brief history of the microprocessors, especially classified as generations of the microprocessors. So the first generation between 1971 and 1973, which used PMOS technology and was not compatible with the TTL. Right? So they were able to successfully produce 4-bit microprocessors, just about 16-pin ICs. And then they were also able to come out with 8 and 16-bit microprocessors and having about 40 pins. They were all found application in toy industry. Most of the time they were used in toys and small industrial applications. So second generation, starting from 1970s, just see generation when you say, normally it used to take decades, minimum 5 years or so. But you can see just in a span of 3 years, so much of development has happened. So technology migration from PMOS to NMOS technology, which helps in faster speed, higher density, that is high packing density, small form factor devices. The most importantly, it was compatible with the TTL family, transistor and transistor logic. So by then, people were producing 4-bit, 8-bit, and even 16-bit microprocessors also came into existence. So they were designed to access a large amount of memory in terms of kilobyte, of course, not in terms of gigabyte and terabytes that we use today. So kilobytes. And it also helped to connect with the I/O ports. So the microprocessors were designed to get interface with the external world entities like through the keyboard, visual display, LED, sound, etc., etc. So these are all the features. So this was one of the very, very popular processors by the Intel 8085. Most of the universities in India and abroad, still you can see that the microprocessor subject. This is being taught, even though this is no more produced by Intel because it is 40 plus years old processor. But it is still being taught in the curriculum. It is still included in the curriculum, mainly because the architecture is so simple and interesting. So the beginners can do a lot of experiments. They can very easily understand the assembly language programming, especially and so on. That's being Intel's 8085 processor, which was maybe a very popular 8-bit processor. It never found application in the general purpose computers, but it was used widely in various industrial applications, industrial homemade appliances and all that. Then slowly the technology increased. Third generation during 1978 migrated into HMOS technology. And again, improvement on the speed, higher packing density, minimum data bus width was 16-bit microprocessors, and extensive instruction set So people used to call it as a complex instruction set computer architectures in the computer architecture perspectives, CISC architectures. So many features it has provided, and one of the representative microprocessor was this Intel's 8086, which was a 16-bit, very popular 16-bit microprocessor. Um, Both internally and externally, we could work with 88, 16-bit data transfer was made possible. In fact, a small variant of this processor called 8088 was what was used in the IBM PC. Only after the development of Intel 8086 in 1978, the computer industries came out with the design of personal computers. So by then, computers were there, but they were classified as mainframe computers, mini computers, and so on, microcomputers and all. So not an individual could afford to have a computer of his own by then. So after this 8086, in the year 1978, I think the year was 1982 or 84, when the IBM came out with the first personal computer, which used initially the 8086, and then they found there was a difficulty for the other designers to use. So they have modified the architecture so that it was compatible with the contemporary 8-bit controllers. So 8088 was used. And then very fastly, many features, many dimensions have been increased. The fourth generation very quickly started in 1980s. So low power version of HMOS technology was adopted, and microprocessors have emerged as 32-bit microprocessors. And then we have even the physical memory space was increased, as I just now told, when the computer hardware came. So when people started using that as general purpose computers, there were a lot of applications. The programmers came and then they came out with different dimensions of use of the computers. That is why it was called the general purpose computer. It was not an embedded computer, right? So the complete hardware was available. So understanding that, people came out with their own ideas, transformed them into the programs, softwares, application software, and system softwares, etc., etc. So when many programs came into existence, there was a need for increasing the physical memory space also. So, for example, this 8085 processor was able to access only about 64 kilobyte of memory. 64 kilobyte of memory is nothing today. Just 64 kilobyte of memory. Right, and then after two generations of the computers, they were able to take it only to 16 MB. Right? Yeah, this 8086, 8082nd generation, they were able to make it as 1 MB. That is 1024, 1024 kilobyte. Nearly 16 times. 16 times greater than that of what its predecessor has had. Even, when software industry matured enough, they found there were a lot of bottlenecks. Physical memory space was not sufficient. And then the next versions of the computers started increasing it. Even they came out with a very interesting concept of virtual memory, apart from this physical memory. So by which they were able to take it to 1 terabyte of memory by 1986 itself. The representative microprocessor is 80386. Right? It's no more, of course, no more available. So it was a very popular 32-bit microprocessor, and it was used in version of computers called PC-80s, advanced technology. People called it as personal computer advanced technology in those days, 80386. So it was the cost of that machines using 80386 was very high in those days. And then likewise, there were a lot of technological revolutions taking place in terms of memory space, physical memory space, database width, the clock speed, and so on. Then the fifth generation of the computers started using the Pentium, again from the Intel computers. Basically, it should have been named as 80. It became as 80486. It was about to be changed to 80586. Then there was a problem in the copyright laws. So the copyright laws of US did not permit the companies like Intel to copyright these numbers. They had to start give such kind of names and then take operate from then onwards. In fact, it is basically in the evolution of the Intel 8085 processor, I would say. So likewise goes. So what is inside of a microprocessor? It's a very generalized thing. Any microprocessor should be having, as I told you, an arithmetic logic unit. So that is where all arithmetical operations like addition, subtraction, multiplication, division, comparison, logical operations, which is higher, which is smaller, whether equal or unequal kind of decisions could be taken using the combinational logic that is already here. And the status of the result were indicated using the register called flag registers, like whether it resulted in a zero quantity or a non-zero quantity, whether it resulted in an overflow, whether the resultant was having a carry, whether the number was an odd number or an even number. Everything was indicated by certain flags and such as the processor status word and all that. And then the microprocessors internal to that IC, they have had their own register arrays. Registers are basically a memory. It is used to store some temporary variables. In solving any problem, when we write a program, so what we do is that we assign some constants to a variable and then we keep working with that variable. So basically, registers are the placeholders of such kind of variables. So they were made available inside the processor, but the size is very less. The number of such registers that are available that could be put within a microprocessor core, right, will be very few. A few tens of registers or maximum 100 registers could be put over there. But in reality, so we want to have plenty of storage. It is a storage place where we want to keep our programs and the programs will refer to the data and so on. So we need to have external memory also. So in order to address the external memory, so we will have something called address bus, right? And then these are all available inside the processor core, and then whatever that is taking place internal will be made out also as data. So data exchange from microprocessor to an external memory device, to our external input device, or to our external output device will happen through this data bus. Data bus plays a vital role. The most important register that you can see in a variety of microprocessors is the following. Either it is called as a program counter in Intel 8085 and other kind of microprocessors. Some processors call it as an instruction pointer. Right. So though it is called by different names, so this register is meant for keeping track of the next instruction to be fetched. Basically, what a microprocessor does is that you have a program stored in a memory. Right. So this is say line 1 of the program, this is a line 2 of the program, and so on. So what it will do is the following. So this will be this line of code from the memory will be taken via the data bus, and then it will be put into a unit called instruction unit. It will decode and understand what exactly the user wants to do. The operation will be carried out, and then it will go and pick up the next instruction, decode, execute, and then the next instruction, and so on. Right? So this is a cyclic process. So sequential process also. The program is basically a sequential program. So every line of code will be executed one after another. So these are all very important basic building blocks of a microprocessor, and everything, as I said, will be controlled by a timing and control unit. So the clock source, the crystal oscillator, will be the basis for all these kind of things. So this is what is going to give the timing for all sequential operations. So these are the basic essential functional blocks that you can see in any of the microprocessors. But when you go to a particular microprocessor, many functionalities will be available. This is a generalized idea. So what is a microcontroller? This is the title, the topic of today's session is basically interface standards for the microcontrollers. Right? Basically, a microcontroller is a single chip, right, consisting of so many things. It has a microprocessor. Microcontroller itself is a microprocessor, right? And just now, as I told you, a microprocessor, if you look at here, has only a little amount of memory called as registers. But we want to have plenty of memory. So memory, like for example, storing a program, you need to have a memory. Right? So when you design in those days, before the advent of the microcontroller, telling so there used to be a microprocessor, then you need to put a memory, external memory. This may be a ROM, this may be a RAM, it may be this may be a static RAM, this may be a dynamic RAM, and so on. Right, but everything is external to the microprocessor. That is the point that you should understand. Apart from this, you also need to have some input-output controllers to get connected with the external world. Like for example, the keyboard, mouse, and then the monitor, output unit, printer, sound, your audio device, this earpiece, many things. So microprocessor cannot directly do all these things, so it requires some peripheral. Right? For example, analogous to our human bodies. Right? So I'm able to deliver a lecture. So there is a brain, right? So which thinks how I'm going to present and all that. And it is a placeholder of thing also, memory also. It remembers something. Uh, because it remembers only, I was able to join on time to the meeting. Right? So, but how do I do? I see through the eyes, I speak through the mouth, and there's a tongue, of course, that makes vibrations and all that. And I use the hands and fingers to navigate the sky. So they're all called the peripheral, right? Periphery, right? The external body, right? Which deals with the external world is a peripheral. So it is similar to any computers, any computing system for that matter. Microprocessor is like a brain and it is like the heart. Like without the heart functioning, so we no more live. We are said to be dead. So same way, yeah. So that is what is actually happening. So we need to have a microprocessor. Apart from this, you need to have memory. We need to have several I/O controllers. So the number of the integrated circuitries, the number of components that helps to build a system increases. If it increases, a lot of interconnections, the board size also increases. The system size also increases. So, thanks to the VLSI technology, the research trends that were taking place in the VLSI technology even today, so that has helped the people to house many components and circuitries in single silicon chip area. So that has led to the concept of the microcontroller. Right? So the microcontroller they were able to accommodate a microprocessor. Not only a microprocessor, they were also able to accommodate memory. Right? Single chip. Within a chip, microprocessor, they were also able to put. So there is a need for an external memory, right? And that such kind of memory could be a read-only memory, or it could be a writable memory also. And then, as I just now told, microprocessor is very important. Memory is also very important, and like the heart is very important. Memory is very important, but we need to have organs, peripheral organs, hands, fingers, eyes, nose. All these sensory organs are also required, right? So that only deals with the external world. So we need to have some way to get connected with the external world. I/O ports are also very important. So in those days, that means before the advent of these microcontrollers, only when the microprocessors were there. So the people had to rely on several supporting peripheral controllers to provide these I/O ports. But the microcontrollers today, if you look at any of the architectures, so they will have enough number of I/O ports, I/O pins will be available, which you can configure them as input pin or output pin and so on. Timers play a very important role in any of the system, right? Apart from the clock source, so several things need to be done. Like for example, counting of an event, generating a different tones, speaker tones, beeps, etc. Right? So, or turning on or turning off of a motor or a bulb or kind of appliance that you want to do. So we need to have some kind of programmable timers. So those days it was available as a separate controllers, but today invariably you can see that the microcontrollers also have an inbuilt feature, counters, and external world communication, serial I/O, right? So ADC, analog to digital converters, even the DACs, digital to analog converters, because the world outside of the microprocessor or a computing system is analog in nature. right? So inside the computer, everything is digital. Microprocessor is a digital integrated circuitry. We can only understand zeros and ones, right? But when you come out of the microcontroller or a microprocessor, what we see, what we sense, what we smell, etc., we cannot say it is good and bad only. It's not discrete anymore. It is continuous, all the analog. So when we want to interact with the external world, sometimes we might want to have analog to digital converter. For example, you want to measure the temperature around us. What is the ambient temperature, right? Right. So in the COVID period, you might have seen wherever you go, people will have a temperature sensor and touchless and temperature sensor. It's a classical example of an embedded system where that handheld device is got a small microcontroller. There is a temperature sensor. There is analog visual converter, and everything's available. The person sees, right? So without touching you, so it is able to measure the temperature around you, and then that is what is indicated over there. So all requires analog to digital converter, digital to analog converters, right? When you want to control the speed of a motor, as done in the automobile industries, cars, etc. So that is also important. There are several microcontrollers. In fact, very popular microcontrollers are listed here. 8051, 8096. So if you have any questions, you can stop me in the middle anywhere. And just in case, due to network problem, if I'm not available, one of you can just call me. Sir, I think you are available. Chavan, sir. Just in case, I go out of the communication, please let me. Hope I'm audible to everyone. Am I audible?
Yes, sir.
Yes.
So these are some of the very popular microcontrollers you see. Intel's 8051 family of microcontrollers. Predominantly, it was used in industrial applications. 8096, one of the very popular microcontroller, and they are now no more used nowadays because they are replaced by the other microcontroller families. There is another contemporary competitor for Intel, Microchip. Even today, it's popular for the big series of microcontrollers, peripheral interface controllers, big series of microcontrollers. So many of the industrial applications you can see people will be choosing because when you want to design an automated system, a control system, right? So we have a wide range of options to choose from as a microprocessor. Whether you want to have a microprocessor or a microcontroller, itself is one of the crucial design choice. And after you decide to have a microcontroller or a microprocessor, so which of the microprocessor or microcontroller that's available you to choose? There are many factors in that particular thing. Then we also have a Motorola. So Motorola was a very powerful competitor for Intel those days, but today they have shifted their business. There was a microcontroller family with the 68 series. Right? It was also considered very, very popular and it was widely used. It was taking a major share of the appliances designed those days. And today you can see this is very, very popular. ARM family of microcontrollers. This ARM is an abbreviation for Advanced Risk Machine. Right? So the RISC is an abbreviation for a term called Reduced Instruction Set Computer. Reduced Instruction Set Computer, which is an opposite term for Complex Instruction Set Computer. Right? So when microprocessors have started evolving, as we've seen in the first slide and second slide, first generation, second generation, all that. So they have expanded in terms of the speed, in terms of the data bus width, in terms of the address bus width, the memory address capability. And apart from that, they've also enriched various instructions, right? The instruction set was also enriched. So the designers came out with new kind of instructions that facilitated programmers. For example, multiplication, there was no instruction in Intel 8085. Intel 86, there was an instruction. So in those days, if you want to write program in Intel through the Intel 8085, if you want to perform a multiplication of some two numbers. Of course, that's a mandatory thing. No? Many a time we'll come across. But we need to do it as a repeated addition only. So subtraction, in division, there was no instruction. So we need to do it through as a repeated subtraction. Right? Even though there is an alternate method to do it, it was taking a lot of amount of footprint, memory footprint, and it has also caused delay in execution of the program. So it was not suitable for real-time applications and all that. So the microprocessor manufacturers have concentrated on that particular thing. They're also enriched. So complex, those class of microprocessors, which has produced hundreds of instructions to user, was called as a complex instruction set computer. But later, through the research, people found that why to keep so many number of instructions? Hardly ever, if you take a statistical survey, people have noticed that only 30% of the instructions of the entire instruction set was frequently used by the programmers. The remaining 70% of the instructions was very rarely used by some programmers. The question is why? So what? The answer is that if you want to include an instruction, you want to facilitate an instruction, that means that requires some space in the silicon chip area. That requires some specialized hardware. It's a hardware implementation, right? Some circuitry is available there. So once you want some space for the circuitry, the size of the IC increases and power consumption also increases. Many things. So people thought, okay, they're all good for the general purpose computers. There it started two classes of things: general purpose computers versus the embedded computers, the embedded systems, embedded computers, right? So general purpose computers like the laptop, personal, the desktop that you are seeing in the colleges and all that, right? So we have complete hardware. We have plenty of memory. You can do many things. There is an operating system like Windows or Linux, etc. is available. But if someone asks what for you're using the computer, what would you say? We say that I'm using it to play songs, to watch movies, to browse internet, or to use Tally, to compose a letter, to write theses, and so on. So there are many things. There are many things. No? General purpose computers, the name suggests, are meant to do wide range of applications, whereas embedded computers are not like that. For example, an air conditioner, a television receiver, a cell phone, mobile phone, right? A washing machine, many things, water heater, etc. You want to see, we need to have some kind of control, digital control over there. But for that control, we need to have a microprocessor or a microcontroller over there. But the application is focused, right? So the application, so if it is used inside air conditioner, probably it has to adjust the temperature, it has to respond to the remote from the user. That's all. Not it is not used to listen to songs, watch movies, and all that, right? So its application is narrowed down. And so what happens is the microprocessor or microcontroller is fixed inside that unit. It becomes an invisible computer, right? Invisible computer. So the last class, Gunasudri madam, I think she has delivered lecture. I've also listened to her talk. So she has referred to a quote from Mark Weiser. So he said, technology should create calm, right? So it should not reveal its existence. It should make no noise. So that is the actual concept of the embedded systems. So for any automated applications, there is a small computer which is almost invisible to anybody, but it will be functioning. So in such kind of things, we use microcontrollers, such as this kind of things. So there the question is that we want to make it as small as possible, and it should consume as low as power, because they're all typically operated with battery and all. So the people have shifted their concept from complex instruction set computer to the reduced instruction set computers. In fact, there was a company called ARM Holdings. So they came out with their own microcontrollers. LPC214X series is a very popular microcontroller. Today, if you look at the research survey and all that, 60% of microcontroller share is taken by these ARM controllers only. The remaining 40% only is taken away by Intel and Philips and so on. supplement. So this is a classical example of microcontroller architecture, especially Harvard architecture. Harvard architecture, where it separates instruction memory into from data memory. So originally, in a one Neumann model of a computers, you might have noticed that there is a memory, there is a ALU, there is a controller, but we can see that starting from the microcontrollers onwards, they were able to give two different memories, one for the program, another for the data memory, and it was largely found used in controllers like big family of the microcontrollers. So this is a classical example of 8051. So as you can see here, there are many functionalities available here. So as I told, there is a processor here, CPU is a core part of it, and inside the IC you have many things, I/O ports, as many as 4 I/O ports are available, and there is a serial communication, and there are a couple of timers, timer 0, 1, and optionally there is another timer also. And then you can see it has got built-in memory. So there's 256 bytes of memory, and there's an interrupt logic here. Yeah, so everything is driven by this crystal oscillator source. Everything is driven by a crystal oscillator source. So some microcontroller also has got built-in ROM. Yeah, it has got a ROM also, as many as 8 kilobyte of ROM is available. What it means is that when you want to design a system, an embedded application, and if you are familiar with this 8051 architecture and instruction set and all that, it's only the matter of writing the program. You just have to use only one controller. If your program can be confined only within a maximum of 8 kilobytes, if you don't require more than 4 ports, that is 4 into 8, 24 I/O lines, 32 I/O lines, if it is sufficient for you, then you can use only one microcontroller. That's the whole idea about it. So it has changed the way the embedded systems have started using. So there's a PIC family of microcontrollers. The PIC has got a wide range of 8-bit, 16-bit, 32-bit families available. This is a classical example of a 8-bit architecture. So why I'm showing is to tell you that this single chip IC has got several number of things. It has got a flash ROM, and it has got a power. There is instruction decoder, control timing. This is a microprocessor. There is an ALU, right? This is a ALU, and it has got a built-in timer. It has got electrically erasable and programmable read-only memory. So your program code can be put over there. It has got I/O ports also here, right? General purpose GPIO we call it as. That's also available here. So everything is bundled and it's available in a single chip, maybe 24 pin or 32 pin or 40 pin IC. So we can design the entire system. This is an example of block diagram of LPC 2148, as I told you. LPC 2148 ARM family of microprocessor. Very rich, as you can see here. Even it has got many functionalities. We are going to discuss about this I2C bus, USB, SPI, UART. There is a real-time clock, and it has got its own bus called AMBA AHB, high performance bus, which is its own ARM version's own microcontroller architecture. It has got a static RAM, it has got a flash memory, right? And then very interestingly, it has got different types of timer called capture and compare modes, timers. There is a built-in DAC. There is a built-in analog to digital converter. In fact, I think there are 5 such analog to digital converters available over there. There is a general purpose I/O also, which provides several number of I/O pins also here. So all in single IC. So here also, if you want to use this, you should have thorough understanding on the instruction set and its internal architectures, register model and all. If one is well versed with it, they can immediately use this and then design their own applications. So what we have seen so far is about a quick overview of what is a microprocessor, what's the difference between a microprocessor and microcontroller, some representative microprocessors and microcontrollers. So now we will shift our attention to I/O devices. So I will not talk much about the memory devices because In these 2 hours of lecture, we cannot cover everything. I just wanted to throw light on interfacing with external world only, right? So interfacing with external world requires, it's a very important terminology, I/O, I/O. So I/O stand for input and output. This is output. So input and then output. Right. So how do we do that? So we need to have again some kind of, as I told, analogous to our human body. So we need to have hand, arm, fingers. There are many things through which we communicate. Likewise, for a processor to get connected with the external world, it requires a lot of devices apart from the memory. Right? So we call them as I/O device 1, I/O device 2, etc. Any number of I/O devices may be available. Right? So multiple I/O devices may be connected to the processor and of course to the memory also via a shared bus. The bus is a group of signals. So basically, it carries some information. Group of wires carrying some information such as the address, data, and then some control information. So accordingly, we call them as address bus, data bus, and then the control bus. So from the name itself, you can understand every device can be uniquely detected by an address. Because when we say there are n number of devices and the bus is shared, so if some information is going on, the processor can only select only one of the devices, not more than one device at a time. Right. So every device should be associated with some kind of address. Right. So that's the idea. So it is address bus which does that. But to access an I/O device, the processor first places the address on the address bus, and then the device recognizes. It should be able to recognize. Maybe it can respond to it, acknowledge it. Otherwise, it can take part in that. And then, what kind of response it need to be done is typically done by the control signals. Right. So when we say that I/O devices is very important for making the computing system, right? So in the I/O devices also there will be some I/O locations, or you can say there will be some registers. There will be some registers available within every I/O device. It's like a memory, right? So if it is a memory, if it has got its own register, this should also be addressed. Right? So there is a very important concept called mapping, right? Mapping the devices. Mapping refers to mapping the physical address space of a processor with the local address space of the devices. For example, a device number 1 may have only 4 registers. Device number 2 may have, say, some 16 number of registers, right? Whereas the processor can address up to, say, 64 kilobyte, as I told you from 80 to 64 kilobyte. Right? So there is a huge amount, 64 kilobyte of space is available. Now the question is, how do I associate this for device number 1? How do I put this 16 bytes of memory location for device number 2 and so on? Right. Right. So the same address space, the entire address space need to be effectively distributed to the devices without any conflict. So how do we give it? So in some microprocessors, there were a concept called memory mapped I/O, and then there is an I/O mapped I/O also. This is the second phase, I/O mapped. That is, the available address space can be given some space for I/O devices and some other space for the memory. Right? That is called memory mapped I/O. So from the programming perspectives, the I/O registers will also be treated as memory devices. That's one form of a thing. So predominantly you can find that in Intel family of microprocessors like Intel 8085. It is there, Intel 8086 it is there. Right? And suppose that you don't want to trade off. I want to give the entire memory space for the memory only. I don't want to share the memory space with the I/O device. Then there's such a kind of memory scheme is also possible. That is called as isolated I/O. Otherwise, it is called as I/O mapped. So a point that you should remember is that every I/O device will have its own registers that need to be given some unique address space. Then only when the processor addresses them, the device can respond to that. So you see that there are address bus going, there are data lines, there are control lines. Three different kind of buses go. And for example, an input device has got its own input IO interface, which will have its own data and status registers. There will be some control circuits, and of course, a very important component is address decoder, which decodes the address bus, which understands operation to be done through control and some amount of information what need to be conveyed between the input device. For example, keyboard is an input device. So when I hit a key, so the corresponding ASCII value or corresponding key value need to be sent to the host program. So that data will be going. And of course, some kind of status register will also be. Status will tell whether the operation is successfully completed or some error has happened. Kind of things will be. So the rate of transfer to and from IO device is very, very important. Right? So it is relatively slower than the speed of the processor. So what it means is that here we are seeing the processor communicates with the memory, which is the program available, data is available. It is also going to converse with the IO devices. But the IO devices are sluggish in performance. The microprocessor can do, or as you can say, the microprocessors can do million operations per second, MIPS, million instructions per second. Just in a blink of your eyes, you could complete as much as 10 lakh instructions in just 1 second. Whereas input output devices are not like that. It will take its own response time. So they are very sluggish, right? So most of the time. So to deal with such kind of speed mismatch, the processor can do several things in just 1 second, whereas its potential is blocked by the slow peripheral device. So how do we deal with very interesting concepts, or the program control IO, and then interrupts and direct memory access. Right? So in the program control IO mechanism, processor would repeatedly monitor a status flag, whether the device is ready or not. If it's not ready, wait. It's like in a software we do like this. Is ready. Is the device ready or not? No. Then again wait for it. If it is yes, then only to do some kind of operation. Right. So this is program control. So what happens is that this would offset the performance of the processor. Riz would say processor is underutilized. You can do during this waiting time, processor could have completed millions of instructions, but just because an input device or output device that is being addressed is very slow, it is also slow down. So the solution is that you can either have an interrupt driven or direct memory access. So you can see that every processor would be facilitated with interrupts, right? One or more number of interrupts will be available over there. So when multiple devices use interrupt, that is the case. For example, in a computer, so in the laptop through which I am delivering my lecture, the laptop or any other gadgets that you are using in your premises to watch the lecture, right? We have several functionalities, right, which will be using the interrupts. There will be a single processor in your computer. There will be multiple programs running, right? So when the programs are running, the processor can execute only one program at a time. Please remember, right? Processor can, because it's a sequential machine, right? So the devices, for example, the keyboard, for example, the monitor, not the monitor, some other device like the printer, right? Ethernet cord, right, etc. Whenever they are ready with some data to be passed on to the corresponding program, they will raise an interrupt. Like for example, I'm now taking a class. So if someone wants to ask a question, so there is a provision here. There is hand raise, right? So that will bring my attention. I'll stop my lecture and then see, okay, somebody is asking. So like that in a real classroom also, it's a virtual classroom. In a real classroom also, when you're delivering a class to the students, what will happen is that some attender or some pew may come with a circular, so you'll knock down the door. Then I have to stop the lecture and then I talk to him and then attend to him. So like that. So the slow peripheral devices can utilize the processor to use interrupts. So interrupt-driven data transfer. It's a very interesting concept. So whenever an interrupt comes, immediately the program is stopped. Then it goes to another part of the program where handler will be available, which we call the interrupt service subroutine. the processor will be executing one after another. When it sees when it sees the last instruction of the subroutine, most of the time it is written, the program will resume where it was suspended. It will resume to execute. So what you can see, the processor is either executing this program one or this interrupt service subroutine. It never takes rest. So the interrupt-driven data transfer helps in dealing with slow peripheral devices. That's a very interesting. So there are several you know uh, aspects with regard to how to handle the interrupts and all that. For example, if more than one interrupt is available, what would happen? So some priority need to be done, right? So whether the processor is now being interrupted by a device, so the interrupting device might want to know whether it has indeed recognized it or not. So we have some mechanisms called acknowledgement, right? So the processor may issue an acknowledgement signal to the device, and then device can respond. So these are all some of the design aspects of the interrupts. And sometimes in a program, you might want to execute a program without any disturbance also. For example, here exactly I'm doing. Right. So what I do is the following. So now I'm delivering a lecture. So I don't want someone to interrupt me. If some phone call comes, it will be an interruption. So I just put it in the silent mode. I also lock the door so that nobody can enter into my room. So likewise, when a critical part of the program is being executed, if you think that that program should not be interrupted, because if it is interrupted, there will be a delay from one operation to the next operation, right? If the delay is undue, then it will result in some havoc. So it should be prevented from. So if you want to do that, if you want to conceal the processor, if you want to hide the processor from being interrupted by any other devices, we have mechanisms called interrupt enable or disable. You can disable some of the interrupts, and then you can re-enable them whenever you can do that. These are some of the interrupts. Then, as I told, when multiple interrupts are there, so which one need to be serviced? These are all interesting questions where basically they are addressed by polling mechanisms, some priority association mechanism, first serve mechanisms, and all kind of things will be done. Yeah, so I just skip on these interrupts. I will focus on the interface standards. So these are all the answers to the interrupts. Yeah. So interrupt plays a very, very important role. In any computer architecture, if you see, in the original IBM PC design, it had facilitated as many as 8 interrupt levels. That means 8 different units like the keyboard, serial communications controller, printer, port, etc. were facilitated with some interrupt. Right? The advanced technology ATI just now I told you. If you look at it has been increased to 16 from 8 to 16. That be the case in the general purpose computers, but in the real embedded applications, right? There may be need for 50 to 100 number of interrupts in a system. Several small functionalities. For example, in automobile industry, in a car, very costly cars, where several functionalities are being controlled. It requires several number of interrupts. So interrupt handling itself is a real great things. So some priority arbitration will be done. So these are all some of the mechanisms that are. It's a trade-off where we assume that there is only one interrupt line and there is only one interrupt line. So some kind of priority arbitration. So which one need to be given due importance. There are some of the interesting aspects for the designers. There is also another interesting scheme called daisy chain mechanism, where the interrupt acknowledgement is not directly connected to every device in parallel, but sequentially. So the device which is very closer to the processor will enjoy the highest priority. If it does not have anything to be done, then only the interrupt acknowledgement will be passed down the chain, down the chain. So these are all some of the arbitration mechanisms. The next very important type of data transfer from the processor to the input-output devices is the direct memory access. It's another very interesting concept of the direct memory access (DMA). So just now we have seen that the input-output devices are very sluggish, right? Very slow, relatively slow compared to that of the processor, right? So we went for this interrupt-driven data transfer with the idea of increasing the CPU performance. So there is another class of devices which normally get connected with the computer is a secondary storage. In any system, you can notice that you either will have a hard disk or in the past there was a floppy disk drive. Right? It's a secondary storage. A huge amount of application program or operating system need to be downloaded into the main memory. So when that need to be done, normally what happens is that the data goes to the processor and then only it will go to the memory. Similarly, from the memory, if you want to transfer to this, it has to go to the CPU register. From there only it has to go to the. So that was the case. So people felt if you want to transfer a block of memory from one secondary storage to another memory, what is the need for involving the microprocessor for the mere data transfer? Is there a facility that we can transfer data directly between memory and the secondary storage bypassing the processor? The answer was this direct memory access concept. That's a solution. Okay. So whenever the direct memory access is required, there will be another bus master, which will release the microprocessor, which will make the microprocessor to wait, and then it will deal with data transfer directly between the devices. That's the concept of the direct memory access. So just for the want of time, I skip the inner details of this. The concept of the DMA is that you can see here, the DMA controller, right, can be used between secondary storage such as the disk and the main memory. It can be used between network interface controller like LAN controller also. It can be used. And in fact, in the modern pieces, you can find that there is DMA controller associated with the printer also. Because today the printers or high-speed printers, they would also require DMA. They're also using. The keyboard, you can see there's no DMA logic because the keyboard is a classical example of a very sluggish input because it's a human operated device. Human responses will be in the order of milliseconds only. So there is no need for faster attention of the device. So there's here again, when multiple devices wants to use the bus, which one need to be given is addressed by a technique called bus arbitration. So there are two classifications. One is centralized arbitration, and another is a distributed arbitration, where there is no need for any single point of entity for arbitration purposes. The devices among themselves will do that. So this is a classical example of a centralized bus arbitration, where you can see there is a processor and the two DMA controllers. The arbitration goes with respect to which of the DMA controller is going to gate the bus and release the processor through some arbitration signals such as the bus busy and then the bus request signals. So these are all the techniques about how exactly centralized arbitration is taking place. Whereas a distributed arbitration takes place among the devices itself, right? So every device is associated with the ID number, 4-bit ID number. Right? So there will be some control signals, and with these control signals, they will be exchanging their ID numbers, the arbitration lines, and they're all connected to the pull-up resistors, and these inverters are called as open collector outputs. Open collector output. That is, they are not TTL. Normally, all the ICs will have TTL output. So, open collector outputs need to be connected to the VCC through a pull-up resistor. Means that you can see that this signal is connected. For example, yeah. So, this signal can be connected with more than one signal. This line again is connected to the two signals. Right? So this is not possible with the TTL. This is possible only with this. So by this arrangement, right, the device A or some device which is wanting to gain the thing will be able to find whether it is granted the bus or not. Right? Distributed arbitration. So they devices among themselves exchange their device addresses and then one with the lowest address which wants a bus request will always win in this particular concept. So this is about the DMA. There's a direct memory access between the memory and I/O devices. Now coming to the bus, just now we have seen bus, the importance of the bus, right? The processor, main memory, and I/O devices are all interconnected by the bus, as I told you. Right? So classifications of the data, address of control signals, and data transfer between the bus, between the devices among the bus can be classified broadly into two categories: synchronous and asynchronous. So synchronous means that both the devices, processor and the device, understand the timing with each other, right? So a huge amount of data can be given. So only the address and command need to be given, and the data burst will be sent, and everything is synchronized with respect to some time intervals. That is the case with the synchronous bus. So synchronous bus requires strict synchronization among the devices, whereas the asynchronous bus doesn't require much of the synchronization. So I would say otherwise, all the internal data transfers, that is inside the system between the microprocessor and memory, right? Most of the time, they're all synchronous bus. Very rarely ever, there will be some I/O devices which will also conform to this synchronous bus, but it would require some synchronization subtlety. On the other hand, when it is not possible for the device to be as fast as that other processor, there is a mismatch. The only viable solution is asynchronous data transfer. Right, so that means we need to have some kind of handshaking mechanisms, some kind of signaling mechanisms like that. So the one that sends at the high speed is called master, and the one that consumes data is called as a slave. So we need to have some signals called master ready and slave ready kind of signals are all available. So in this classical handshake protocol, the master places address and the command information, then assets the master ready signal. It is high level. All devices on the bus decode the address that have been placed over there. Address slave performs, requires operation, other things do nothing. Master removes all other signals from the bus once the slave ready is asserted by the device. So then the data transfer will be taking place over there. So the point that you should remember here is that whether it's a synchronous bus or a data bus, asynchronous bus is always shared. We cannot have independent connections between processor and every input and output devices, right? Which is not a viable solution. So when the bus is shared, especially the data bus is shared, how to make the devices understand that the processor or the master is indeed dealing with that is a very important question. So this is a simple comparison. Advantages of the asynchronous bus is that it eliminates a need for synchronization. It can accommodate varying delays automatically using this slave ready. Whereas the asynchronous disadvantage also suffers from the following. Data transfer rate with the full handshake is limited by 2 round trip delays because the signal has to go from device 1 to device and then it has to come back. That's why it's called 2 round trip delay times. If the distance is more, the delay is also going to be increased. So it is well and good if the proximity is very closer. That's what it means. Yeah. So we normally use these address data and control signals to address a particular device through a port. The ports themselves can be divided into two broad categories: the parallel port and then the serial port. Right? Parallel port and the serial port. Parallel port means that all the data, either 8 bits wide or 16 bit wide, are transferred at once from one system to the other system. That means we need to have as many number of wires as possible. Right? This is a classical example. So you can see here the data. Maybe it's an 8 bit or a 16 bit. Everything is connected at once. So this is a external world kind of thing. So data comes and resides in a data register, and then there's a status indicator, status register will also be available. So all these things are viewed as registered by the processor. It will address when the data will be collected over here. So the data transfer takes place parallelly, and that is why it is called the parallel port. But the advantage here is that because all 8 bits or all 16 bits comes at once, very faster. But the disadvantage is that if one or more number of lines are broken, right, and it will cause erroneous data being transferred, and it is not ideal for long distance communication. Just for want of time, I just skip all these kind of things. The intercases of the parallel port. So the point that you should remember here is the following. We always need to have a latch for designing any output interface. All the output data need to be latched output. So we can see that this is a classical example of a printer port. Right? This is a classical example of a printer port. Printer data is going. So when within a system, when you want to transfer some ASCII data to the printer, we cannot directly take it from a system. It is a system data bus, but it need to be latched through an outer latch, and then this is sent. This is controlled by the entire control circuit like this. Right, and you also need to have some kind of handshaking signals that runs between the host system and then the printer also. So idle says that okay, the bus is idle, right? And valid is a command from the host system, the printer saying that I have placed a new data, take it like that. That kind of handshaking need to be done. This plays a vital role. So this is considered to be a register, one location. This one location need to be mapped appropriately in the address space of the processor. So we need to have an address decoder. As you can see from here, the address decoder takes one or more of all the address lines, A0 to A13 in this case, properly decodes for a particular pattern, and then it is going to trigger this. So we need to have that kind of understanding. Because it's only a 2 hours session, I'm not able to give you very detailed in design practices. Because the intention of the lecture is only to throw some light on the importance of address bus, data bus, and control bus, and then some standards. So I just look at this kind of things. Yeah. The next type of data transfer is a serial. As I just now told, parallel data transfer is fast. Advantage. Disadvantage is that not suitable for long distance communication. When the two systems are say some 10 meters away, right? Then the long wires that are connecting from one system to another system will seriously cause attenuation of the signal. So you will not be able to reliably send the data. So where you want to have relatively a long distance communication, serial port is the only viable thing. Even though it basically offsets the performance by bit communication, bit by bit per communication. So there is only one line. So information has to go like this only. Whereas in the parallel case, we have D0, D1, etc. going all at once. So very quickly you can do. But now, first D0 goes, and then D1, then D2, then D3, and so on and so on. So naturally, there will be a slowness in the communication, but with reduced number of lines connecting, and those lines can be, signal conditioned. So it can be boosted. The signal can be boosted at the transmitter. It can be downsized at the receiver. Very interesting. So this is finding a lot of applications, especially there are UART, universal asynchronous bar receiver transmitter. So we'll have input shift register, output shift register, serial input data, and serial output data. So all of them are connected to a system data bus like this. And it will have its own registers, chip and register select address, status and register, control register, etc. will be available. The rate at which the data is shifted out is typically synchronized with respect to the receiving clock and the transmission clock. And in the literature or the technical specification, it is called as a baud rate. Rate at which the information goes, expressed in bits per second. How many bits per second can go? There are some standard bits per second, such as 9,600 bits per second, 1,200 bits per second, and so on. So here again, the speed is inversely proportional to the distance. If the distance is more, the achievable baud rate is very less. If the distance is very less, we can push the data at a very high speed. This RS-232C is a very popular standard. RS-232C, recommended standard. There are many standard organizations. So one of the very famous standards setting thing is EIA, Electronics Industries Association. Has got several standards for various applications. RS-232C is one such standard from EIA, Electronics Industries Association. So which was called as a COM port, COM export, COM1, COM2 port in the computer industry in those days. Before the advent of the USB, these COM ports were the telephone line, modern, many devices were connected with that. This is a classic example of the connectors, DB25 pin D-type connector or a 9-pin D-type connector, right? So in the modern PCs, you will not be able to see, but if you are able to see some personal computers or laptops purchased some 5 years ago, at the rear side, you can see at least one or two number of connectors will be available to these connectors. So even though you see 9 pins that are available here, there is only one line on which the information goes. Transmit data, and another line through which data is received, to receive data. It is like this. Yeah, it's mentioned here. From data terminal equipment to data communication equipment, from the data communication equipment to the data terminal equipment. So the communication aspects, it's called the full duplex communication is possible with independent lines for transmission and reception is possible. And these are all some of the modern control lines, CTS, RTS, request to send, etc. They are available in those days. This is I2C, inter-IC, right? Inter-integrated circuitry bus, right, was predominantly developed for microcontroller families. Only in the embedded applications. You cannot find this in the personal computer applications. Of course, it was developed way back in 1982 by Philips. Now it's called NXP semiconductors, right? So this idea was very interesting. This helped giving a synchronous data transfer. Whereas RS-232C is a asynchronous communication. We need to have handshaking for every character oriented, but here it's block oriented. The interesting idea is that it has got only two lines called STA and SCL, right? Serial clock and then serial data. Only two lines. With these two lines, you can connect with multiple. Basically, it's a bus arrangement. You can have multiple devices can be connected with this. Very interesting concept, and this is being used to connect EEPROMs in the microcontrollers. EEPROMs in the microcontrollers. So this shows how exactly ICs can be connected. Various ICs can be connected. The master-slave concept. So here in this notation, there is a master. So you can have several number of slaves. They are all connected in a bus type. And it has got its own detailed protocol and bit identifiers, device identifiers, and all that. As you can see from here, you can have 7 bits or 10 bits. That means it supports as many as 2 power 7, as low as 2 power 7, or 2 power 10 different devices can be connected in just a couple of wires. So if you understand the I2C protocol, and today invariably all the microcontrollers come out with I2C bus, which is a programmable bus. So you can, with a minimal number of wires, you can do a lot of data transfer. Very interesting. So these are the standard I/O devices. These things were used inside the personal computer. So far we have been talking about computer to external, and another communication is that between a processor and internal components. So we have had things called PCI bus, peripheral connection bus, then SCSI, small computer systems interface. SCSI is pronounced as SCSI, and today we have USB. The latest bus standard is the USB. So I skipped this PCI because it's only internal communication. So I will discuss only about. Uh, so I'll just skip this because it's only internal communication or interfacing with the memory and other kind of things. Yeah, SCSI bus, small computer system interface, was devised for connecting with this is an interface card for connecting with secondary storage devices like hard disk or CD-ROM drives, especially more than two number of hard disks, up to 7 number of hard disks can be connected with this video. And it's also very fast. Data transfer rate is also very fast. So if you ask me whether it is a serial communication or a parallel communication, undoubtedly it is a parallel communication, right? Which can transfer data as much as 5 megabytes per second. 5 megabytes per second communications possible. So it comes with 40 pins, 68 pins, or 80 pin wire connections. And you can find this kind of SCSI bus interconnections in server applications. In your institute or in your some other thing, if you see the use of servers, you can see the SCSI hard disk will be predominantly used because they are not economical to be using desktop computers and laptop computers, whereas a desktop computer and laptop computers uses only AT attachment. This is a new name for IDE controllers, integrated drive electronics, which is extension of the address bus, data bus, interrupt and DMA controller signals directly from the motherboard into the hard disk. That kind of mentions was there. So this diagram shows like the interface between the CPU memory and several things. It can be a hard disk, it can be a printer, it can be a CD-ROM drive. So you need to have a controller for everything. And one shared bus will be available. Everything will be connected over it. The point that you should remember is that it's a parallel communication. These are all about the protocols, so just skip because of the amount of time. Here, there is a notion of controller, initiator, and the target. The devices are classified into 3 categories. These are the steps, and it also supports DMA. These are some of the very important signals. For an 8-bit bus, DB0 to DB7, and of course there is one more bit called parity bit for error detection and error correction. And these are all the control signals. They tell whether it's a data or the control information or a message information that goes on the bus. So this is and today, as the technology increases, people always want to go away from getting connected with many number of signals. They always want to go with very fewer number of signals. So they want to use the concept of IDE. They want to use the concept of SCSI. At the same time, they want to minimize the number of things connecting the hard disk and other devices. So everything has become serially attached. ATA called SATA. This is an example. And then serially attached SCSI bus called SAS bus today. So again, in the servers, you can find predominantly this kind of connectors will be available. So inside the device like hard disk or the CD-ROM drive or the printer having this facility, you can see that there will be a lot of conversion, serial to parallel and parallel to serial conversion taking place, and then only the IDE protocol or the SCSI protocol. Next in the line is a USB, Universal Serial Bus. It's an industry standard, right? Developed by several companies like Intel, Lucent Technologies, Microsoft, and so on and so on. With an objective that, we have serial COM ports. The number of COM ports are limited in any computers in those days. And the number of devices wanting to get connected with the computer, the host, was enormously increasing. The people found, 2 devices are connected with the ports because RS-232 supports only one connection. So 2 devices are connected if there's one more device I want to connect, where do I put it? So that was the question. So that has triggered the idea of USB. People came out with, as the name says, universal. It should be universally adapted. And it should be a bus type that where you can just plug and play. And it should be serial data transfer because it only helps in doing minimum number of players. So we don't want to have it connected with so many number of players. But at the same time, it should also support moderately good speed. So the USB supported, as well as 1.5 megabits per second. Please remember, just I told you, RS-232C of the past supported a maximum of 115 kilobits per second only, and this is like 1.5 Mbps, nearly 10 times better than this, nearly 100 times better than this. And as much as 480 megabits per second is also possible today. USB 3.0 supports even more than this. So serial communication with thanks to the trends that are taking place in what they call now the information theoretical approaches has helped in coming with a lot of encoding standards which matches to that of the parallel communications. That is why people are going for the serial communications. Right? So basically, it's a plug and play. It has got only 4 lines, on which 2 lines will carry the data, and 2 other lines are basically the power. And the bus is extended through a hub concept. There will be a root hub, and then you connect another hub. From there, you extend it. Finally, it will go to the IO devices. And the specification says that you can go as many as 127 devices plus the host computer. Right? So you can connect as many as 127 devices through USB port, and then you can achieve different types of data transfer speeds. And it has got its own applications, a wide range of applications, for example, the keyboard, internet connection, speaker, anything, even the pen drive. So today you can see that USB ports have completely replaced the conventional, I would say, the RS-232C port, COM ports, otherwise they're called as, and then the Centronics ports, printer ports, because through this USB, because it's plug and play and is always compatible, devices once attached, what type of device can be easily identifiable by. So it's not only the hardware specification, but it's also doing something with the device specifications. So that's interesting. It has got its own protocol, right? So message transfer will go here on the bus structure. There are different traffic classes here, isochronous, and all that. The very important electrical characteristic is that it has got 2 lines, 4 wires, of which 2 of them are used for the power. And of course, the power is required only for bus powered devices like pen drive and other kind of things. If it is self-powered device like printer, etc., only 2 lines called data plus and data minus will be sufficient. The signaling here used is differential ended differential ended connection is what is used here. Right? That is, you have data plus and data minus. There is no TXT and ground as in the case of RS-232C. So there is no ground reference. So we have D plus and D minus complementary with each other. So that they're all they can be found used in general purpose computers as well as in the embedded applications. In the embedded applications, the industry came out with its own bus standard called CAN bus, which is called the Controller Area Network. Controller Area Network. Basically, it's like local area network, and in the ISO protocol stack, is much similar to the physical layer and data link layer. So you will have a lot of CAN transceivers, especially in the automobile industry. So that will be able to connect with many number of devices in using this CAN bus cable. The other interfaces are wireless. So far, we have studied about the wired, majority of the wire. Wireless, right, gives a lot of applications for the users. We don't have to be tied with the wires. The solutions are again Bluetooth, which gives as much as 1 Mbps, but it's a short range communication. Wi-Fi gives as much as 12 Mbps, relatively a long distance communication. But when you are concerned with conserving power also, there's a Zigbee standard today. It has come, right? Transceivers are all available, with which it is working with 2.5 2.4 gigahertz ISM band, right? So you can construct any embedded application with just this ZigBee interfaces, where using which wirelessly you can transfer with a moderately high speed communication. This is also possible. So those are all the interface, different types of interface standards. I also wanted to say on this because this is also a very interesting. It has gone a very interesting evolution. The display interface standards. In fact, it all started with the. Should be this. It all started with composite video. Composite video. In older day computers, if you look at the computer video was connected as a composite video where it is basically an analog superimposition of um, the intensity, the horizontal synchronization, vertical synchronization that is required for deflecting the beams in the CRT. Everything is made composite and just a couple of wires it will be going. But people felt that clarity was not there. The clarity was not there. The people wanted to have high resolution display, digital display. Right? So that they came out with color graphics adapter. Then it came out with VGA. This is an example of that. The 15-pin connector, where it gives distinct signals called blue because RGB, the spots make combination of the RGB makes different possible colors. All of them are zero corresponds to the black, and all of them are 100% or maximum value corresponds to the white color. So with the number of distinct levels, it's possible. So SVGA, all these signals are driven as analog signal. Analog, it's not a digital signal, analog signal. So inside the controller display adapter, you can see it will have a display memory where every color can be indicated by 8-bit word or a 16-bit word. So 8-bit means 2 power 8. So 256 into 256 into 256. Color space is available. That's why we say millions of colors possible for this VGA color standards are possible here. Apart from this color intensity, you also have two horizontal signals for horizontal synchronization and vertical synchronization. So this was an evolution. And today you cannot, you can rarely ever see VGA connectors. My laptop has that. But in the modern laptops, you rarely ever see that. And today what you see is HDMI. Stand for the high definition multimedia interface connector. This not only delivers high quality, high definition video output, but when you say multimedia, it also talks about sound also. Even the sound is also deliverable. So between the monitor or between a television, which is compatible with the HDMI, we deliver VGA-like video signals with the synchronization, as well as digital audio also. Digital audio is also possible. And it supports maximum as much as 2560 plus 1600 pixels. So detailed display is possible, which was not possible in the predecessors. So this is another interesting revolution that has taken place with respect to the interfacing of the monitor industry is considered. Well, I think we are on time. So, so what we are seeing for the past 1 hour and 15 minutes of time is about the evolution of the microprocessors, right? So microprocessors way back in 1970s and then evolved in different dimensions, memory addressing capability and all that. And the theme of today's topic was introducing different standards, interface standards for interfacing the microcontrollers. So I have focused only onto that, microcontrollers, distinction between a microprocessor and microcontroller. I've given you some sample microcontrollers. In fact, there are hundreds of different types of microcontroller families available. These are purely a design choice, right? So as a designer, as an electronics engineer, so we need to come out with an application that we have to decide whether we are going for a microprocessor or a microcontroller. If so, which of the family? So am I knowledgeable in that? Is it a good candidate for this particular thing? All that The next question is like we have to decide upon a memory, uh, how to interface that memory mapping, etc. And then very important thing is interfacing with the external world. Whether we need a timer, whether we need a general purpose IO, serial IO, parallel IO, everything is required. Right? So we should also have a fair idea about the standard protocols, standard specifications such as RS-232C, Centronics, USB, CAN bus, Wi-Fi standards, etc. So all those things have been detailed in this 2 hours of lecture. And what is very important is that the USB has completely changed the way the interfaces started working, right? And we have not seen an alternate to the USB as of now, right? USB is still evolving only. The alternate to the USB could be seen only through the wireless capabilities. Today, people hate wired connections, so we go for wireless. Even the wireless connections come with wired fidelity connections, so people go for that. And again, for the display also, the trends starting from composite video to CGA, color graphics adapter, and VGA, and then we have HDMI interfaces. Even in the same line, and today people are least bothered about connecting a device to a projector or a video monitor or a television through the cables. We always want to connect wirelessly, and today the wireless technology also permits that. Many technologies, screen sharing, everything has come to existence. So I think in this past 2 hours of discussion, I have done my best to give you throw some light. Even though I have a lot of slides, the time did not permit, and I didn't want to go in depth also. I just wanted to throw some light on the various aspects of I/O interfacing and existing standards. Thank you all for your patience listening. And if you have any questions, I'm ready to take them. Thank you.
Thank you, sir. Thank you very much, sir. From audience, any queries? Some faculty members are here who is teaching microprocessor, microcontroller.
Very
They
good.
also can ask. They also can ask some questions.
Yeah. Yeah. Can you please introduce what teaching microprocessors? I'll be glad to meet you. And I also want to know like what kind of microcontrollers you teach in your curriculum.
Alok Kumar Jain.
Yes, sir. Hello.
Please.
हाँ sir.
Any queries?
Sir, no sir actually.
Okay, I
Basic
will ask you. Hello,
microcontrollers
Kumar. Okay, hello, Kumar.
Yes, sir.
I will ask
Okay.
you. Yeah. Just I'm keen on knowing. Like, so what are the controllers you are in your curriculum for the BTech students, and what are the facilities that you
Sir,
have?
actually, I'm
Yeah.
not taking any lectures, but I will.
Okay.
I do the lab actually the third year student. So in
Okay.
that, we will actually performing the experiment in
Okay.
yes, sir, in Texas kit. Actually, one
Okay.
Texas kit is given. So
Okay.
the
DSP. Okay.
actually, uh, and I'm using actually the software for
Okay.
yes, Texas instrument given by the one software that is
Okay.
yes, sir. And in that, we will actually do the experiment like LED blinking in
Okay.
LED
Okay.
blinking and related, and also the synchronous motor. We can connect with that, and we can
Very good.
change the intensity of the actually LED, and
Okay.
also using the push button actually experiment.
Very
So,
good.
sir, that's all actually for the lab experiment. Some also microcontroller, sir, also doing the experiment with
Okay.
sub 8051 microcontroller kit,
Oh,
addition,
very good.
subtraction, multiplication, division, like that actually.
Very good.
These are
Very
the
good.
actually curriculum in BTech third year.
Okay. Okay. Very good. Very nice to hear about it. So still you are teaching 8051. So my suggestion is that you can always move on to the latest microcontrollers like ARM controllers, because 8051 is considered to be relatively obsolete. It is no more in production, and it may be easy for teaching and it may be easy for the beginners. But if you look at the immediate use of it, you will not be able to find the microcontrollers in the market. On the other hand, if we introduce this LPC 214 it's a series of microcontrollers, they can have hands-on. Immediately, they can build projects also using such kind of.
Yes, yes.
Yeah, consider upgrading your syllabus also. Thank you, Alok Kumar.
Thank you, sir.
Okay. Shraddhanand Verma, you may also ask some question. Shraddha. Okay, no problem. Okay, sir. Thank you very much, sir. And this is the time of vote of thanks also. Then I am thankful to Director IT Lucknow, Mr. S.K. Paliwal, sir, for his kind support to organize this IT lecture series by IEEE student branch. Thank you to our head of electronics engineering department, Mr. Neelam Srivastava, madam. He is always motivating to do this lecture series he was telling from last time. And I'm thankful to all the faculty members, students who are attending this lecture. Today strength is very less. I think students are busy in their GATE examination. But this recording will be available with them so that they will be benefited by this. Okay. I'm thankful to our speaker once again, Professor K. Selva Raju sir, and from PEC, Pondicherry. Okay, sir. Thank you. Thank you very much, sir. It was a very nice lecture.
Yeah, we will keep in touch. Yeah, so in future also, if you want some special lectures for your students, I am eager to do that. Thank you, sir. Thank you very much. Have a nice time.
Thank you. Thank you very much, sir.
Bye. Thank you all.